Okay, so good evening, everyone, and welcome you all to this online interactive lecture series, which are being organized by the INO project now for many months. We are almost on the, I guess, about 50 talks have been held so far in this series, and you probably heard most of them. And in case you missed some of them, as we always announced, all the videos of these talks are available on the INO project YouTube. And the slides of almost all the talks are also available at the portal, whose address we keep sharing with you on the INO project webpage. We can also probably share on the chat window today. As we just now announced, so this is the last talk in this series of where we are having weekly 3 lectures per week kind of thing. And from next, that is September, we are going to have these talks on every Monday at 6 p.m. So we have one talk per week on Monday at 6 p.m. So let us come back to today's talk. It's titled as Programmable Electronics and Applications in High Energy Physics. This is going to be delivered by my colleague, Ms. Mandakini Patil, from Tata Institute, TIFR, Mumbai. Just take a minute to introduce today's speaker. Mandakini did her MSc Physics with Electronics from Mumbai University, and before she joined TIFR, she actually did, she taught for a year or so in the SIS College, Mumbai. Okay, she of course then joined TIFR in 1990. Initially, she worked for a year or so in the low temperature physics group at TIFR, and subsequently joined where she is right now, the experimental high energy physics group. And this is how it was called those days. But of course, now it is called the Department of High Energy Physics, where she is now a scientific officer F. She was involved in the, very actively involved in the CMS, so-called outer hadron detector. It's called HO detector for installation, commissioning, and testing, as well as the silicon strip detector R&D for another accelerator experiment in Japan called Ballet experiment. She is currently engaged in the CMS HCAL upgrade electronics. That is the CMS experiment, and the HCAL is the name of the detector, and CMS trigger upgrade electronics. And today she is going to talk about the role of programmable electronics, that is mainly the field programmable gate arrays based in particular, and their applications in high energy physics using the CMS trigger system as the case study. So with those few words of today's speaker, I now invite Mandakini to start her lecture.
Hello. So am I audible?
Yes, Mandan.
Yeah. Thank you, Satyanarayan, for the kind introduction. Yes, me to give this talk. I feel privileged to be in this list of speakers when I know that good elite speakers have joined this forum and have been talking on very interesting topics all throughout. Basically, I'm going to talk about the programmable electronics, and with a focus on its application in high energy physics, and more in particular about the CMS and the LHC based CMS detector where I have been actively contributing. So I'll just take 2 minutes to switch off the video, and then I'll start sharing again. Just give me 2 minutes. Yeah. So as is conventional, I'll start by giving the outline of the talk. So I'll be mostly giving an overview of the programmable electronics, and in particular the field programmable gate array. I'll talk about what is the hardware description language, which is basically a means of communicating with this hardware. And I'll just give a flavor of what are the different variants of the HDL, but more I'll be stressing on its application and how it works and all that. I'll also talk about why we are using FPGAs in the high energy physics, and especially in why we are using FPGAs in the CMS front end, the back end, as well as the trigger boards. And then I'll just summarize and just for completion talk about the general application of FPGAs. So,
Mandakini, we don't see if you are on the slide 2. We are still on slide 1.
okay, just now
Yeah, we are still on the opening slide.
I can see slide 2 here. Can
Uh,
you see now?
Not really. Maybe it requires you to kind of unshare and share it again.
Okay.
Okay, now you can pick up your slides. Yes, now we can see your outline.
Yeah.
But
Yeah. Can you see now?
yes, yes, this is
Yeah.
now slide 2.
Yeah, slide 2. So, just as I was talking on slide 2, I'm just giving a conventional way of giving the starting the talk by giving outline of the talk. I'll be giving talking about the overview of the programmable electronics, and with a focus on the field programmable gate array. What and how, what is the hardware descriptor language I'll talk about, which is the main means of communicating and working with FPGAs. I'll also talk about the motivation of using these FPGAs in high energy physics experiments in general. And later I will focus on the case study, that is FPGAs used in the CMS, both as well as in front end, as well as back end, as well as trigger electronics. And then I'll complete by talking about the general applications of FPGAs. On slide 3, so basically when you talk about LA electronics, I just want to recall how the microelectronics has really evolved. As you can see here, the first picture shows the wall transistors, basically the vacuum tubes which were used which we started using the transistors as. Then came the solid state transistors. The solid state transistors along with the passive components then miniaturized, and we form circuits. Then you can see the first multi-transistor silicon here. Can also, I mean, after that, many of these transistors finally were embedded or with the VLSI technology. They were all packaged, and we got the pack logic or the gate. So you can recognize here the 7408, the low power Schottky and NAND gate here, which will be, I'm sure many of you would have used in your college days. And of course, on the last image is the mini processor board, on which you can see on multiple integrated circuits connected. So this is how the transistors evolved with time, and basically the driving technology was the nanometer CMOS technology, which gave rise to more advanced digital electronics. So when I say I'll be focusing more on the digital electronics. Of course, when I say microelectronic, it involves transistors, forming amplifiers, and analog circuits also. But today's focus, I will try to keep on digital electronics. So I'll just walk through what were the options for building the digital circuits. So you can see that on the first image, you see a discrete components being wired on a breadboard, which finally started getting soldered on a printed circuit board. And then, of course, more advanced things took up, and we started building application-specific integrated circuits. So what is application specific integrated circuit is nothing, as the name suggests. It is an integrated circuit which is basically used to particularly perform a particular application, and it is meant for doing that functionality. In addition to this, coming to the latest thing, so what is different on the third part of the image that you see here? You can see that I am showing here the again the integrated circuits, but they are slightly different in their look also, and they are basically the field programmable gate array. The one of the things which also distinguishes here is the FPGAs are, you can see a grid that I am seeing showing here. So basically, these FPGAs are actually mounted with a new surface mount technology, that is the ball grid array technology, wherein the underneath of the IC is used to make connections, and in the form of a grid, you can see that. And then the solder is basically in the form of balls, and then it is pasted one to one with to the printed circuit board. So this ball grid array technology is also used for mounting the microprocessors on the PCB. So the advantage of this is basically you can have more dense interconnections, which will otherwise be very difficult and may not be reliable if we go to manual soldering. So, trying to understand what were the options, what are the building blocks of the digital circuit, and on slide 5. So, I'm just talking about the various units or the smallest components of a digital block. So, you can see that we have basically the logic gates, OR and NOR, NAND, and all those. You can have wires to interconnect them, then you can have simple switches to disconnect this wire, and of course we can also include a D flip flop. I have included a D flip flop, which is basically a memory element that retains the state of the input signal and then transmits it to the output. And basically it can be implemented in the form of registers, flip flops, random access memory, and its basic functionality is to store this. Now, what happens and how do we go ahead and make the digital logic block programmable? So, what will happen if you try to make each of this building block programmable? So, that is what I'm trying to say on my next slide. That gives rise to what we call as a field programmable gate array. So, what is a field programmable gate array? So, a quick answer is that it is an integrated circuit and mostly digital electronics. Of course, I have come across the recent documents where I have reports of a lot of analog interfaces being added to a FPGA circuit. But as of now, I have not come across an analog circuit really implemented in the form of a FPGA, but it is more of a ADC high-speed interfaces which are integrated to form part of the FPGA. So it is mostly digital electronics. And why do I say it is programmable? Because it is not programmable inside, it's outside the factory. So hence the name field programmable. And what describes how do we communicate with this FPGA? Basically, we design the circuit and in the form of the schematics, or it can be specified or with a language called as hardware description language. Of course, I'll be giving the details of this. So now when I said that I can program all the digital blocks which build the FPGA, I need some tools to compute this programming file for the FPGA. So basically the FPGA is configured with the design, and then your circuit is ready to use. Of course, I'm going to elaborate more on each of this thing that I have talked about. So in short, to a layman, I can say that you can uh, build your electronic circuit with an FPGA without using a soldering iron and without plugging together the existing modules. That is without having a chip produced at the factory. Of course, it is a chip produced at the factory, but mm, we are altering with the hardware itself, level itself. So to more elaborate it, you can see what is inside FPGA. So you can see that FPGA basically the simple FPGA architecture is shown here. There are many simple programmable logic blocks which are actually essentially logic gates and flip flops. And then it has lot of programmable switches that you can see here. It has many wires. You can see by the solid lines that I've shown here, both horizontal and vertical. So what does the FPGA designer do? So you can create a complex logic circuit just by programming the FPGA. So over the years of these digital blocks, more and more powerful functionality is added. That is in the form of phase lock loop, random access memory, multipliers, CPU, and serial deserializer. So in the context of high energy physics application or use of FPGA, we tend to use lot of serial deserializer blocks of the FPGA. Of course, most of the other things, the clock multipliers, the random access memory, and the programmable logic things that are, of course, part of it, and we use that also, programmable logic blocks. But I'll just elaborate more on this next slide about what is a serializer and deserializer, because we are going to use this within our systems. So basically, a deserializer is a is a pair of blocks which is commonly used in high-speed communications. So what happens here is when you're transferring digital data, one block is basically converting the parallel data into serial data, and the other block is converting the serial data into parallel data. That is why the name serializer and deserializer. So this allows a lot of bits transmission using a small number of FPGA input output. Another thing I should stress here is FPGA, the basic potential is whenever I'll try to use FPGA in those applications where the parallelization is more important, and that is where exactly our detector data acquisition systems are designed around that. I mean, you have lot of input output channels. So wherever you're looking for lot of parallel input output connections, there you can think about using an FPGA. So normally the serialized signal is sent out via a differential pair of wires, basically two electrical lines, and it has control characteristics. Sometimes the differential electrical line signal is converted into optical signal. Again, I'm talking about this because we are going to touch upon this, and this is how we are transmitting the electrical signal over long distances in our data acquisition system. So the details of the serial deserializer are really more complex than what you can see in the picture. But basically, you have to know that FPGAs are having inside the serializer deserializer blocks. And of course, there are other features which I already touched upon. So the evolution of these features began, the FPGA was first invented in 1985. So initially it was basically a mesh of loosely connected logic blocks. That is what you can see. And then slowly, with that advance in technology, some of the block got also got converted into a random access memory. The RAM block got introduced, and soon after that, you can see that lot of programmable IO pins have started coming here, which is shown at the periphery here. And then you can it also started having a lot of clock management and access cards, access block units. So soon after that, realizing that it can the whole FPGA can include many more electronic units which are frequently used, so just like the DSP slices, that is the digital signal processing slices. Then another most important thing that is being incorporated in the inside FPGA right from 2002 is the multi-gigabit transceivers. This is again a feature which we are exploiting in our FPGAs that we are using in our systems. So you can see here that the yellow part that I'm seeing here, the multi-bit gigabit transceivers are seen. Also, it started having SoCs or microprocessors and system on chip. It started having Ethernet MAC units, and then of course it also started communicating with the external world through the PCI interface, and it also had some part of system monitoring thing that you can see here. So basically, how does
Mandakini,
yes.
can you please take a question right now? There is a question from Shubham.
Yes.
Yeah,
Yeah,
Shubham,
sure.
can you ask your question?
Yeah, hi, can you hear me?
Yeah,
Yeah,
we
I
can.
can.
Yeah, ma'am, on your last slide, you talked about serializer and deserializer. How is that different from an encoder?
Okay, basically, when you're saying it's a kind of encoder only, you can say, where different bits of data are being either multiplexed or demultiplexed. But here you can see that we are using a differential pair of way of transmitting the sequence, which in a way reduces the electromagnetic noise and by doing this kind of thing. So and basically you can say that the encoder and decoder is basically together embedded and formed into a serializer block, and it is placed as a pre-configured circuit inside a FPGA.
Okay, thank
So
you.
yeah, more or less it's kind of same thing.
Mandakini, another question from YouTube. I mean, if you want, you can postpone it for later. But the question is ASIC versus FPGA, which to choose and why?
Yeah, I'm coming to that in my
Okay,
next
fine. Okay,
next
fine,
slide.
fine.
Yeah,
Okay,
yeah, I'm
fine,
coming to that. Yeah.
fine.
So basically, very often we know that we use CPUs for programming and also GPUs. So why do we then you need FPGA? And what is the comparison in terms of performance? So I'll just point out here that of course when you are talking about floating point number crunching and all that, CPU has an advantage. Sorry, and programming a CPU is definitely much easier than a programming an FPGA. It does not really need to have a pre-hand knowledge of digital electronics. But of course, now programming a FPGA is also become relatively simple with higher level languages are also coming into picture, and we don't necessarily have to learn the hardware descriptor language. But relatively, definitely, it is true that programming a CPU is much easier than programming an FPGA, because in while doing a programming of FPGA, you definitely need to have some background of your digital electronics and how you can implement the logic in the form of gates and all that. Also, CPU you can do faster compilation. The code portability is also easier, and unit cost is lower. FPGAs come with having a
The code portability is also easier.
also FPGA advantages is it is definitely better with multi-clock systems. So whenever you are talking about a complex data acquisition system and lot of electronic modules, like what I told earlier also, whenever the parallel input and parallel outputs are being considered, FPGA definitely has a higher place compared to CPU. It does parallel processing, more parallel inputs outputs are there, and it does flexible processing, and also the timing operations are better here. The comparison for GPU versus FPGA will be same as that of CPU versus GPU. So what is general thumb rule is, if you can reach all your targets of the floating point operation or whatever you want to do within a CPU, then you can use a CPU. But if you cannot, then you should consider a GPU or a FPGA. Of course, I'll stress more. I mean, I'll come in my forthcoming slides. I'll talk about more advantages of FPGA, because we are actually directly interfacing with the hardware. We are trying to build the circuits without a soldering, and I mean that point I think is a very good point. If you are a electronic or digital circuit designer, you will realize that just by clicking few lines of code, you are actually able to implement and wire and dewire the what is there inside a FPGA. So that is an advantage. I'll talk more about that to stress on the usability of FPGA over CPU and GPU. Yeah. Okay, so there are various types of FPGA. As I told you, it is the interconnect mesh or the wire which is also being programmed inside a FPGA. And the technology that is used in programming this element actually is important. So there are three different types of technologies which are used. One is called as the anti-fuse or a non-reversible. So this is more or less now slowly getting obsolete, but of course in some of the FPGAs they are used. So this is a one-time programmable thing, and it uses the non-standard CMOS process. So I think CMOS process, people know that complementary metal oxide semiconductor technology, which is the basis underlying technology for all integrated circuits, silicon or germanium, mostly silicon technology. And of course, but it is mostly the traditional technology is mostly monolithic, whereas in FPGA it need not be monolithic. It can be multi-layer also. It can be what we call as a silicon stack interface can be used, SSI technology that they talk about. I won't go into the details of that, but if there is any question, then I can answer that later. Of course, there is the second technology that is used, that is the static random access memory technology, where the register cells are used. This also again uses the standard CMOS process. So SRAM technology is definitely the fastest technology, and you can see here on the right side I have also named the major manufacturers of the FPGA, major vendors or the major players in the market, the Atmel, Intel, Lattice, and Xilinx. Of course, Microsomy and Aeroflex, these were some of the companies that were using anti-fuse technology. Each has its own advantage. Anti-fuse technology based RAMs basically are more reliable because they are just you do the programming only once. SRAM is definitely fastest. It can be programmed, reprogrammed again and again. But there is one disadvantage of SRAM is it is not as power efficient as flash technology. The flash shells again uses a non-standard CMOS process. It uses cells with floating gate, and here the power efficiency is faster. So flash, though slow, it can really build FPGAs which can consume very low power of the order of microvolts and all that, microwatts and all that. But in SRAM technology, also I read a paper recently. I mean, lot of new things are coming up to actually make it more power efficient. I mean, the transistors which are used inside, what they are trying to do is they are trying to keep use dual transistor methodology, wherein one transistor is switched off and one transistor is partially on to initiate the logical switching and on, switching off and switching off power at power on. And also they are coming up with multiple actually VDD, that is the power supply for powering the SRAM FPGAs. So they are using low voltage power supply for some part of the circuit to power some part of the circuit, and still lower for some part of the circuit. So this kind of mixed balancing of techniques is making SRAM technology more popular, and it is also becoming more power efficient. But definitely flash is preferred if you are really going for low latency and so you can see that Microsemi is one of the very popular company which has come up with which uses flash things. So here I can also mention that there is a family of FPGAs which are classified based on the number of logic elements that are there inside that, number of pins, number of powerful logical elements like multipliers, CPUs, and all that inside that. So they are classified into different families. So Microsemi has one FPGA family which is called as Igloo family, and this Igloo FPGAs are used in some of our CMS detector hardware electronics. It again uses flash freeze technology, and because of this flash freeze technology, it is able to enable the entry and exit from the low power mode, and while it still is able to retain the SRAM technology and registering data information part of that. So you can have a mixed technology also. So igloo FPGAs are famous for that, and Microsemi also has come up with radiation tolerant FPGAs. Of course, radiation tolerant FPGAs are very costly compared to the commercial FPGAs. So if they are absolutely needed, they are being used in many of the detector based or high energy physics experiment. As far as other companies, I have actually Altera. I have missed here. Not missed actually. Altera and Lattice. Sorry, Xilinx are now some two of the very major manufacturers of FPGAs, and in fact, you can say that more than 70% of the FPGA market is captured by them. Altera is taken over recently 2 years back by Intel, and Atmel Lattice are not so much heard of, but okay, some of the earlier days they were coming up with the same. But the major player now, as of now, you can say is the Xilinx. So basically, Xilinx and Intel or the Altera FPGAs and the Microsemi FPGAs, you'll be hearing these names again and again as I go on with my slides in the subsequent part of the talk. So, what are some of the large FPGAs that Xilinx has come out? I'm specifically focusing on this because this is again something, a choice which was made in our CMS trigger experiments. So you can see that, like what I told you, basically FPGA is a fabric of loosely coupled logic elements or the lookup tables, and the registers, the RAM components, the digital signal processor blocks, the multipliers, and so on, and gigabit transistor. So here you can see that some of the largest FPGA device can contain as large as over 1 million input lookup tables. It can have 2 million registers. It can have thousands of block RAM components and DSP block units. It can have up to 96 multi gigabit transfers, and of course, it also has many other factors. Of course, larger the FPGA, larger will be the cost, and you can see on the right hand side, with the evolving technology, the family of FPGA has upgraded. So starting seen here on the right hand side is the 65 nanometer technology, which started. That is when the Vertex 5 family was started by Xilinx FPGAs, and later you can see that. Which add up to something like 330,000 logic cells. So the capacity went on increasing, and you can see that Vertex 6 had almost double the capacity of logic cell from 330,000 to 760,000. And now you can see that with the advent of the 28 nanometer technology, the Vertex 7 family has roughly about 2000 K logic cells. So that's how the FPGAs have progressed. And of course, now we have FPGAs which are classified as ultra scale, ultra high FPGAs. I'll be talking about that. So those are the FPGAs which are really expensive, and but they are more powerful, and hence they serve the purpose when they are being used in high end electronics when we need it. So, sorry. So coming to, sorry, I think I missed the comparison of FPGA versus ASIC. I'll come back to it. It should be there somewhere. It's probably sequentially not arranged. So what do we do? How do I talk with an FPGA basically? So the FPGA vendors give you various tools which can be used to start designing your circuit. And this design flow, basically the steps that you see here, you can see that the design entry is the first step. After that, wherein you write the code in the tool provided by the vendor, either in the hardware descriptor language. Now I'll just come to what is hardware descriptor language, and then the next step is you synthesize the circuit. So basically, when you write the code, it is being translated into a gate level circuit inside, and then we try to map and do the place and routing. So what is the meaning of this? So suppose I want to build a adder or a subtractor. So there is a pre-configured logic unit building block inside FPGA. So I am trying to actually map to the resources, and I will try to place the wiring such that I'm able to realize that adder or subtractant using the pre-configured logic block which is there inside the FPGA. So this routing and placing definitely needs optimization, and this optimization is computational hungry, and that is why it does consume some power in this process. So that's why some of the FPGAs require higher power. But of course, I mean, like what I told you, there are flash FPGAs which are flash freeze technology based FPGAs which are consuming lower power. And the last stage is once you have placed and routed, and you have what we call actually generated a net list where we are actually mapping the input output ports, and you're ready to connect your FPGA to the external world or the sensor or the electrical signals. And after that is done, the optimization of the mapping and placing and routing happens. After that, what we do is we program the FPGA. So the programming can have like the SRAM technology uh, is will not be able to program. I mean, once it is powered on, you'll have the program written, but once you power it off, it will not be there. So normally a EEPROM or a SD card is used to download that program into a FPGA, and after power on also you can continue to do the programming. So I'll just explain this three steps once again in the subsequent slides. So what does a design entry do? Basically, you can use various techniques. You can actually, the tools that are provided by the vendor, there is a methodology to actually place the schematics, just like how you use this lab view and all that. So you can do that also, or you can write a code through hardware descriptor. It's a bit cumbersome to build or design large circuits using schematics, so HDL is preferred over that. So what happens after the design code is entered? This is a phase where it is actually translated into a circuit, such as gates, flip-flops, multipliers, and also it starts using the registers. So the next step, I have shown that basically we use a design abstraction model called as the register transfer level, which models the synchronous digital circuit in terms of flow of the data signals between the hardware registers and the logical operations being performed on the signal. So RTL is the register transfer level. So you can say that FPGA understands finally the lower level of abstraction, that is register transfer level. So basically your input hardware descriptor language gets converted into a net list, which will list the logic elements that you will be able to will be needing for your project, and then the interconnects that are needed. All this is mentioned in the specific hierarchy. The process will begin, a syntax check will be done, and then you feed your HDL code into your design. After that, there is a optimization by reduction of logic, elimination of redundant logic, and reduction of the size of the design. And while simultaneously it is making it, all these processes make it faster to implement. Of course, the last step is to map out the technology by actually connecting the design, and that is how your circuit is ready to use. So that also involves what we call as implementation and programming of the impingement. That is the next step after the synthesis. So basically, there are various tools by various vendors. So this ISC Cortex is a tool provided by Altera FPGA manufacturers. Vivado and Vivado HLS are the tools which are provided by Xilinx FPGAs. I'll come to that actually. So basically, as I told, after synthesis comes the implementation and programming, where we actually map out the logic block, connecting and placing happens, and the last step is the device programming. So this is finally loading the mapped out and completed routed design into the FPGA. So this is the final step where we need to actually generate a bit stream file. So I think I've already talked about this implementation part in the earlier slide. So I'll just go to the next slide. So what is important to verify the design or the implemented design functionality, which is a very, very important part of FPGA design, especially if you're designing very, very large circuit or a integrated. I mean, this simulation is in fact used in ASIC manufacturing also. So there are a lot of simulation steps that are done. So there is something called as the behavioral or the register transfer level simulation, which is performed before the synthesis at the design entry. So this can be used to basically check the functionality of the design without the constraints. So when I say without the constraint, so it is not specific to your pin number or your make of the FPGA. It can be any FPGA. So this is that kind of simulation. Then after synthesis, you can be verified using at the netlist level. So when you say netlist level, you're actually seeing the pin compatibility and you're adding the constraints into the simulation. But of course, here we are ignoring the timing related issue. Then comes post at the implementation time. Actually, we are also the placing and routing takes place, and this is where the timing simulation becomes important. So what is the delay? What is the latency that is the FPGA is able to give you? What is the time it takes, the speed it takes to implement a circuit. So all that information you get in the timing simulation. So now I have been talking about what a hardware descriptor language is. So it is similar to a programming language, but the difference is it is translating into the gateware, basically the logic gates and the flip-flops, and whereas your normal language is high-level language, programming language translated into machine instructions, which are usually executed by a CPU. So the common hardware descriptor languages are VHDL, Verilog, and there was earlier ultra-specific HDL also. But now with the engineers wanting to program in high-level languages, even newer trends are evolved with C-level, C-like languages, handle C, system C, even Python I know is being used. And this is what we call as high-level synthesis or HLS. Even LabVIEW is being used. So just to give a small snapshot of what code in various, okay, sorry, I forgot to tell that the HDL language, just like your different flavors of programming languages, C, C++, HDL actually comes in two flavors, that is VHDL and Verilog. So the syntax and the methodology is different. Sometimes people prefer VHDL over Verilog, whereas some prefer Verilog over VHDL. So I won't say that it's a matter of choice and what you are more comfortable with. So you can see that Verilog, the module input output, and this is basically an implementation of AND gate that is seen here. So Verilog, it is slightly slower. And in this VHDL, I have shown a behavioral model. You can actually implement, write a code in a gate model also, but you can see that the syntax is slightly different. So you have the list of variables here, and which basically get translated into input or output ports, which is seen here by in and out here. And the and the less than or equal to sign here, the behavioral model describes that finally and logic is being implemented. And same thing, you can see how it looks in C++. So there is a complaint, of course, that we have to learn a new language to be able to talk to FPGA. So slowly this is going, and we are having new tools which can communicate with the FPGA in a higher level language. So why do we need FPGAs in high energy physics? Basically, we know that in high energy physics, detectors and accelerators, we have to use FPGAs and tailor the hardware to your specific requirement. Suppose you have a simple cosmic muon experiment in the lab. So this is just a detector system here shown here, which is familiar to most of you, with two scintillators, a photomultiplier tube, and which then connected into an analog to digital converter, which is then connected to a PC through RS-232. So this is just a simple system here. Suppose I want to duplicate this system, and what is a real complex detector system look like? So it can be a previous apparatus, but it is duplicated thousands of times. So having thousands of computers here becomes very cumbersome. Okay, so how do I solve this? How can I not use a computer and still make a very complex data acquisition system using by duplicating the detectors and the ADC signals? So one way to mitigate this is you can remove all the computers, and you can see that the output of the ADCs, basically all the digital signals, can be routed and can be connected to a FPGA. So the many computers are substituted by a single FPGA. So in most cases, we can buy one or a few FPGAs. Not all FPGAs are very expensive. The lower end FPGAs are quite cheap, and that can serve your purpose here, and you can build a data acquisition system using FPGA. But here I am using a FPGA basically after the ADC. I can also use the FPGA in other control systems also, in the front end part also, where I need to transmit data at higher rate and all. I'll talk about that. So what is a typical detector readout and the data acquisition system? You have a detector, you have amplifier, then comes a filter. So this part, the first few blocks that I have shown here, they are all more related to the amplification and the thing. Once the signal is digitized and the clock comes into picture, then it is a digital signal, and then you can play with that by filtering the noise. You can do zero suppression, you can do range compression and all that, and then you can introduce what we call as a trigger, basically to select the interesting events. So slowly I'm trying to get you familiar with what the trigger logic is. So in our CMS, which I'll be talking about, the trigger levels can be in the form of two levels, level 1 trigger and level 2 trigger. So basically, in the level 1 trigger, there is a buffering taking place, and then in the level 2, you can see that after some feature extraction, again some buffering is taking place, and some formatting and readout is taking place, but a lot of filtering is happening. So this is exactly what we do in our trigger system also. So just to give a application of FPGAs in the high energy physics experiments globally. So you can see that we have lot of other modules other than trigger also. I mean, we have time to digital converters which are used in the data acquisition system. You can have a readout system. So you can have various trigger high level triggering computer nodes that are used in Panda experiment. These are also based on FPGA. So you can see here I have listed the use of FPGA. This is not an exhaustive list. This is just a few instances or examples of FPGAs used almost in all high energy physics experiment, and it can be said that it is really a part and parcel of all the high energy physics experiment, be it the CDF experiment at Fermilab, the Belle 2 experiment at Japan, the Panda experiment at Germany, the Chloe 2 experiment in Italy, and of course CMS Atlas Alice in LHC experiment. So now coming to the case study of CMS. So most of you are familiar what a compact muon solenoid detector look like. It is basically a multi-layered detector with various layers of particle detector, tailored detectors around the proton-proton beam that is colliding. The closest to the beam being the pixel, then comes the tracker and the electromagnetic calorimeter, then the hadron calorimeter, and finally the muons and the solenoid coil. I think my colleagues, Professor Dasu and Jyotsna, have really elaborately talked about the various detectors and their functionality and level 1 trigger. So I'll just quickly go to the next slide. So how do the FPGAs figure in this CMS hadron calorimeter? So you can see that we actually use FPGAs both in front-end electronics as well as back-end electronics, which are the back-end electronics is basically located in the counting room, in the control room, whereas FPGAs lying in the front-end electronics are close to the detector. You can see that in CMS HCAL, a lot of FPGAs were used both in front end right from 2004, and you can see that since some of the FPGAs are exposed to total ionizing dues, this is some kind of the neutron fluence that is to which these FPGAs were exposed. Some of the front end FPGAs, that's why actual anti-fuse things were used, and microsemi flash is being used in the upgrade. In the back end, mostly it is Xilinx and Altera and Xilinx high-end. Some of the microsemi flash-based FPGAs, as I said, are radiation tolerant. Of course, they are expensive. Actually, there is a facility in CERN called as CHARM facility, where this extensive work is being done in close collaboration with the Xilinx engineers, where the physicists and engineers at CERN are also trying to actually test how radiation tolerant FPGA, because most of the commercial FPGAs which are being sold should not be taken at the face whatever is the radiation tolerant level they say they give, specs they give. Now, just to highlight on the FPGA use in the front end electronics. So I got first introduced to FPGA when I started working on the HCAL front end electronic phase 1 upgrade. So you can see there are typical, you can see the HV, that is the barrel hadron calorimeter, and the NCAP calorimeter, and you can see a PMT, but actually it could be replaced by silicon photomultipliers. So this is the front end part, which is shown on the upper half of the signal, the charge integrator encoder, the QI chips, and there is the IGLU FPGA or the front end FPGA, which is basically formatting and aligning the data, and then it is transferring that digital data into a gigabit transceiver, and then it is going to a versatile transmitter receiver, where it is getting converted into optical signals, and optical signals are then traveling to the back end, which are all sitting in the control room. And you can see here the micro heater, that is micro TCA based HCAL trigger readout. The advanced mezzanine card, again, it is a micro TCA based controller card, which is all sitting in the thing. All of these are actually having FPGAs. So when I started working on this FPGA, this upgrade program, that is how I first got introduced to what a FPGA is and why is it powerful. I just come back to the real pictures. So you can see that we started developing and fabricating the front end electronic boards. You can see a calibration unit on the leftmost bottom corner. So it houses a pulsar board, which I am showing on the next page. So you can see that it has the Actel FPGA here. So this is the first time when I started understanding what a FPGA is. Of course, the firmware was already built, so I didn't really have to start writing a HDL program and all that. But even to be able to program the FPGA using the tool, that is how I started learning how the source code is. So this pulsar board FPGA was first used basically for calibrating the LED light. So all we had to do is we had to give a digital signal to the LED to stretch the on time and off time of the LED pulse, and that was done through the FPGA. So basically we could actually reprogram it and increase or decrease the width of the digital signal that was going to the FPGA. One good part of this is also that these FPGAs can also be programmed remotely. So you don't have to actually be having a programming cable or the JTAG cable, that is called, close to the unit. You can also, of course, the efficiency is not as good as that, but and this is one example where I have really started working with FPGA. And on the right hand side, on the lower side, there is a QI board which also hosts the IGLU FPGA, which was mainly for data aligning and formatting the digital data after it was digitized in the QI board, before it was transmitted to the gigabit transceiver. Then on the top side, you can see that I have shown a readout module. The readout module basically houses the QI board. The second module, the clock and control module, CCM, also holds a lot of FPGAs, which is trying to continuously talk and read and write and communicate with the backend electronics. So the backend electronics you can see here, you can see a FC7 board here, that is a front-end controller board. Basically, this front-end controller is also continuously talking and communicating with the readout modules, and there is also a micro HTR trigger readout, which is basically reading out the that is where the input from the ADC digitized input from the transceiver is coming actually. So this is actually a integration of front end and back end that I've shown here, where I have where I got exposure to lot of FPGAs in various functionalities and various electronics boards. FC7 uses a Vertex 7 family FPGA. Sorry. So going back to the FPGA, so I just mentioned here that the Pulsar board has a microsemi FPGA, Igloo FPGA is in the HCAL front-end electronic boards. Microsemi FPGAs are also found in the new generation clock and control module. Then they are also there in the time to digital converters. They are also there in micro AMC cards, and also for data acquisition and control applications are built around the Xilinx Kintex 7 FPGAs. Then, of course, FPGAs are definitely there in various galvanometer trigger and global trigger boards of the backend. So, what is a trigger task in a CMS? Again, my colleagues have already stressed on it, so I think I am running short of time, so I'll try to brief through it. So, basically, trigger is has a task of inspecting the detector information and providing a decision whether to keep the event or throw it out. So, this is basically implemented using FPGAs. So FPGAs have basically revolutionized the trigger system, because the logic or the algorithms they need to be fixed when they need not be fixed when the board is produced. So on field we can actually write the algorithms and try to program the FPGA to the required to build the firmware that are required for the trigger algorithms. I'll come to that. So in the CMS level 1 upgraded calorimeter trigger was processor board CTP7 used the Vertex 7 FPGA as its primary data processor, and this was the first time CMS trigger board was employing the Zinc system on chip embedded Linux thing, which also provided TCP/IP combination. With the higher luminosity and the further phase 2 upgrade, we are going to include lot of tracking information, and that's why the challenge of trigger track finding becomes more, and you have a data detector colliding at the rate of 40 megahertz, but within 4 microsecond, which has now increased to 12 microsecond, we really have to reconstruct the particle track with sufficiently low transverse momentum so that they can be used in the level 1 trigger system. So dedicated all FPGA hardware system is being developed with time multiplexed architecture to address these challenges. So this is the CTP7 card. You can see the Vertex 7 690T FPGA, which basically uses which is actually uses a lot of interface tools again given by FPGA, which is because of which you can actually develop runtime control and use Linux standard communications also, the Zinc FPGA. So it also integrates a eye scanning monitoring thing also, which can be done on easily. So this CTP7 become actually we started getting to understand this calorimeter trigger primitive generation card when we started getting involved in the phase 2 trigger upgrade which we are currently in. So the new level trigger one system, you can see that here the rejection ratio is even higher. The level 1 trigger system has to reduce the bandwidth from to something like 100 kilohertz, and then the latency is increased from 3.8 to 12.5. But basically, and the second level, that is the high level, which is normally implemented in the form of software, has to reduce it to 1 kilohertz. So basically, you are dealing with very high data transfer rate. You have to do lot of filtering, data filtering, and you have to do this all in a with a latency of in microseconds. So that is why you can see here. And this level 1 trigger system has various detectors inputs, the backend calorimeter trigger, the hadron forward calorimeter and the BCT or the barrel calorimeter trigger. Both the HF information and the calorimeter information is finally combined to form what we call as a global calorimeter trigger. And then when you combine with the information from track trigger and muon trigger, you form what is called as a final global trigger after it is getting correlated. So I will not go into the details of this part, but I'll just stress the use of FPGA, where and when, how it is used in the new level 1 trigger system. So basically, we started understanding CTP7, the calorimeter trigger primitive 7 card, and that paved way to the involvement in the phase 2 trigger system, where we started understanding what is a regional calorimeter trigger segmentation. So in the new level 1 upgrade, trigger upgrade, you can see that we have to have information, we have to take inputs from the electromagnetic calorimeter and the HCal towers, and we have to form various clusters or regions, and then finally put some logical cuts, what is the energy that is actually stored in a particular cell, and then we try to merge these crystals to generate what we call as the maximum or the peak energy cluster. So basically, you can see that the block diagram of a regional calorimeter card which does the clustering and the initial calibration looks like this. So you can see that there are 85 links coming from electromagnetic calorimeter, because electromagnetic calorimeter has large input electronic channels. Something like 1700 crystals are being giving you the input signal, and a hadron calorimeter is giving 4. So there are various algorithms that are written inside the regional calorimeter trigger. We try to understand all these algorithms. All this is being done on a 9UP that you can see here. That is Vertex Ultra Scale family 9 of Xilinx FPGA. So this is the FPGA. This is which is at the heart of this RCT card, and the different algorithms which are being developed in high level as well as VHDL are implemented on this FPGA. So we started trying to understand how the sorting of the cluster is happening, how final data packing and unpacking is happening, what are the input links, what are the output links, how the output information is coming out of the FPGA. All this will be appreciated more if you try to remember the fact that finally we are dealing with digital data, and since we have lot of input output links, and there is something called as the algorithms involve basically if but kind of logic decisions to be made when the energy of the particle that is so giving information in the ecal or hcal is above this much pt, this much et, and those kind of if and when logical conclusions have to be drawn. The very obvious choice will be use of FPGAs. So that is why FPGAs used in this trigger board should be appreciated. So basically, what does the regional calorimeter do? There is no sharing between the regional calorimeter trigger. Of course, this is evolving, and the number of links coming from the regional calorimeter trigger and the global calorimeter trigger is all changing slowly. But we are trying to understand what each of this card does. Both of this card, both regional calorimeter and the global calorimeter trigger, are electronic boards which are using Vertex ultra scale Vertex 9 family of ultra scale Xilinx FPGAs. So all the information that is coming from the RCT cards are finally combined into a global calorimeter trigger, which does the stitching of the neighboring clusters and it forms what we call as a physics important detector by triggerable objects. So no sharing or the input happens here also, and all calculations are done inside each card. After the forward hadron and the regional calorimeter trigger information is sent to the correlator, the global calorimeter will combine all this and then send it to the global trigger, that is a GT. So all this has to be done within 12 microsecond, not 4 microsecond. So this is the allocated latency. So all this firmware implementation and has to be, I mean, you have to have a very optimum way of writing the algorithm and see what is the final number of resources and the timing information that circuit implemented in the trigger card FPGA takes. So this is what is being continuously done by us, and we are trying to get involved in the firmware development part. So the new thing that is there in the compared to the old CTP7 calorimeter trigger primitive board, the new thing that is there in the current phase 2 upgrade is we have to work on a advanced processor trigger board which conforms to the advanced telecommunication architecture, which is slightly more complex compared to the micro, even the form factor and all is different, and also more powerful compared to the micro telecommunication architecture, which is the standard backend interface which was used earlier. So here we are using Xilinx Ultra Scale and Ultra Scale Plus families. Even the finally the electrical signal is converted into optical signal. So a lot of Firefly modules are used, which should be able to transmit data at the rate of 28 Gbps. So a lot of 12 transmitters or 12 receivers are there per module. And you can see that some of the transmitter and receiver modules can also go up to 28 gigabits per second. So this is also uses 64, 66 bit encoding, which is used in Ethernet basis. So we started understanding what is this advanced processor based demo card, or the first main advanced processor card, which is now replacing the CTP7, you can see. So it has a lot of other functionality also on this. So a lot of mezzanine boards can be seen here. You can see a lot of mezzanine boards here. So these mezzanine boards, one of them is the embedded Linux mezzanine board, which we have recently fabricated. We have also fabricated and developed the IPMC, the Intelligent Performance Platform Management Control Board, and also the memory lookup table is also part of this. So there are various boards here and FPGAs. These are all receiving signals from the electromagnetic calorimeter, the HCAL towers and all that, and the algorithms written inside this FPGA are basically deciding the various triggerable object outputs for the computing firm. So most of the trigger firmware is being developed in high level synthesis tool. So what is high level? It is an automated design process where it interprets the algorithms we are specifying at a higher abstraction level, and it creates the digital register transfer level code, and it will implement that behavior. This basically accelerates the design time while keeping full control over the choice of your optical architectural exploration, and of course proper level of parallelism and implementation. So Vivado HDL HLS from Xilinx is a very useful tool, and my colleagues and we are all trying to understand how to actually implement the files as an IP block for use with these tools in the Xilinx design flow. Lot of C++ and C library functions and constructs are also there inside the which can be optimized for implementation inside an FPGA. So these libraries basically ensure high quality of results. Now coming to the FPGA applications outside the high energy physics community, this is just for completion. So you can see that there is a list of various fields. FPGAs are basically everywhere: aerospace, medical electronics, ASIC prototyping, automotive data centers, consumer electronics. I heard that it was in fact used by the Apple i7 mobile phones where FPGAs were first used. In fact, Microsoft is also using FPGAs in its data centers, and even Amazon is using in their various cloud services and all that. So basically, FPGAs are also getting more popular for implementing this deep learning, machine learning, and neural networks and all that. And that's why they are also used for various other applications that you can see here: digital signal, video, image processing, computer hardware emulation, voice recognition, and cryptography. Cryptography is basically data mining with machine learning and all that. So it's definitely very powerful and a potential electronic device which has versatile applications other than high energy physics detector also. So I think I can conclude by saying that FPGAs are the powerful programmable electronic chips which have revolutionized the high energy physics DAQ modules. The high-end ultra-scale plus and ultra-scale FPGAs are almost inevitable component of the trigger hardware and the track-finding algorithms in the particle detector instrument. Firmware development has also increased the collaboration of engineers and physicists together, making the complex systems more flexible and reliable. Programming FPGA is now also possible using high-level languages that is C++, OpenCL, and Python. And TIFR, definitely our group is actively looking forward to contribute towards the development of CMS trigger hardware mezzanine boards and also in the firmware that is the algorithm development with some prototypes already delivered and they are successfully tested and installed on the main advanced processor architecture trigger board also. So I think I'll end here. Thank you. So if you have any questions, let me know.
Yeah, thanks, Mandakini, for a very nice overview of both the technology and also the applications, and in particular, the kind of work that your group has done towards the CMS experiment. We have just time for a few questions because we are already 7:18 right now. There are a number of questions on the YouTube. I will take a few of them for you.
Okay. Yeah.
One of them
Yeah,
says,
I
"What
can
is
answer offline also. Yeah,
okay?"
whatever few I
But
can take now, I can take now. No problem.
sure, sure. What is the effect of radiation on the electronic components in the high energy physics experiment?
Okay, actually, I can show you. Basically, any ionizing radiation tries to upset the signal event, or you can say that it changes the bit one to this thing. So what we call is single event effects are seen, which are normally caused by a single ionizing radiation. So I am showing my slide 50 here. So you can see that there are a lot of disrupting of the single event which is manifested in different forms, whereas the bit stored in a memory element itself gets modified. So you can say that a digital signal is temporarily modified. So this happens, of course, when the total ionizing dose is beyond certain value and all that. So defects are caused by those defects which are not actually affecting the CMOS process will not be so relevant for the FPGA. So what is a solution for this? Basically, you can use FPGAs to you can reconfigure the FPGAs, you can reprogram them. Of course, there will be some data loss and dead time will be introduced. So then you can have a radiant tolerant controller part, and which will try to actually monitor when this happens, and you can only reprogram only a part of the FPGA, which is called as active partial reconfiguration. So a lot of research is ongoing in order to eliminate this data loss and dead time using what we call as the redundancy strategies. So that is something, I mean, I have not used, but I have heard there is some technology called as TMR, which I think some of you must have heard, which is tri-modular redundancy technology, wherein there are basically a duplicate of the logic element. So out of the three modules, one of the majority will be used and two of them will be redundant. So when there is any such damage that has happened, then it will switch over automatically to the non-used module, and it will save the data loss.
Okay. Another question that was said is, What is the timing estimate for the algorithm at L1 trigger at CMS for track identification in HLLHC?
Okay, often I may not be able to answer, but it is definitely the reports of the various people working on that, when they synthesize and implement the FPGA, they come out with a report which displays the timing. So I think it is microseconds level kind of thing. I'm not very sure to exactly how much is this thing for the tracking purpose. Actually, it depends on how many clusters you're really combining and forming a track and all. So if you're actually writing algorithm to with a track with a large number of inputs, then of course the time required will be more. So if you're doing it in a part of the cluster, then the time required will be less. But often I don't remember exactly how much.
Okay, another question. These are all from the same participant, basically. There's Abhinav Chaudhary. Is it possible to read back rather, from an already programmed FPGA? This was, of course, answered by another participant, Shiv Shankar. But do you want to answer anything? The answer given was you can read back from the bitmap file if you have programmed into a PROM memory. That, of course, is possible. But I mean, the question could be, can you directly read from FPGA fabric itself?
If you want to read back, I didn't get the question.
No. Is it possible to read back what you actually programmed in an FPGA?
Yeah, actually you can read back. In fact, if you are able to, the implementation actually displays the entire circuit schematic, and you can actually say that which wire is getting switched on, or which is actually getting fused and anti-fused. So that when that displays there, you can actually tell what are you doing. So basically you are reading back what you have programmed. In fact, a snapshot of the entire programming this thing is available as one of the feature of the tool, and you can have a look, zoom it, and you can exactly know which connection is done, what is the input port created, how can it make, you can reprogram it as you output, and all those things. So you can definitely read back those things. The provision is there.
I think you have answered it, I guess, but let me just check. Ashish Patil, are you using any machine learning in trigger logic?
Yes, there are. I have heard about a lot of people using machine learning, basically in trigger learning. But again, you should remember that machine learning is a more of an automatic process, and it's not a dynamic thing. So definitely for those repetitive pattern finding things, you can use machine learning, and it is being used. But what I have heard is with the physics motivation being very stringent, physics objectives being stringent, it will not be used entirely in the trigger logic. It is definitely used in some part of the trigger logic, machine learning, and I think some of the engineers are working on it. But as of yeah.
So maybe we take this as the last question again from Abhinav Chaudhary. So why does resource utilization of an FPGA varies with respect to the input size? Input size, I mean, maybe input signal size or input data size.
Okay, so it depends on what kind of logic you're circuit you're trying to implement. Suppose you want to you implement when you say input signal size, it's not exactly the input level or something. It is the number of inputs, right? That's
Number
what
of
if you are.
inputs.
Yeah. So basically the input pins are close to some of the logic blocks which are pre-configured inside the FPGA. So if you are trying to actually go to those logic pre-configured logic levels which are close to your inputs, you can actually instead of using a far off logic element, you can build for example, you can build a multiplexer using 2 AND gates or 3 AND gates, depending on how many inputs you want to actually multiplex or demultiplex. So if you have a larger number of inputs, definitely you will have to use more switching logic, and that is why it increases the number of resources. Again, the timing will get affected depending on the floor plan. I mean, how close is your logic element being used to your input levels. But the resources will get affected depending on the larger number of inputs, because if you want to build say 5 to 1 multiplexer, so you have 5 inputs and you have to just select one out of the 5. So definitely the encoding logic that you are going to use there, encoding will require more number of gates, right? You can't have a 2 input AND gate work as a 3 input AND gate. So you'll have to build a 3 input AND gate. So that is why the resources will increase with the number of inputs increasing. I hope that answers.
Yeah, I think so. Also, I do see Professor Kajari Majumdar has also added some comments to some of your questions. You must have already read them. So that kind of brings me. There are no more questions, Mandakini. So I would like once again, on behalf of all the participants, both on Zoom and YouTube, would like to thank you for taking your time and very nicely bringing out the technology at hand, which is namely the programmable electronics, but how it is making a big difference to the modern high energy physics experiments and also some other applications beyond that. So thank you very much for your nice talk.
Thank you.
Yeah, thanks a lot. Yeah, bye-bye.